It's amazing what we can do with networking today, isn't it? And this is all really possible thanks to a suite of protocols. What does that mean? Many different protocols all working together to bring these amazing networking capabilities to our systems. The suite of protocols is known as TCP IP. There's Transmission Control Protocol and Internet Protocol, but these are just two of a whole bunch of protocols that work together to make this miracle of networking happen. In this nugget, I want us to roll up our sleeves and start to see elements of this TCP IP suite on a Windows system. So do a search on your Windows system for Control Panel, and you're brought here and you see there's this network and internet area. And notice that we can go in and we can view the network status and tasks. In here, notice we can go up and we can change our adapter settings. The network adapters are what allow us to connect to these various networks. Here you can see that we're connecting through Wi-Fi, and if I right-click this Wi-Fi connection and choose Properties, we are brought to this Wi-Fi Properties window, and notice there's Internet Protocol version 4, and we can go in and we can look at its properties. The first thing I want you to note is there's two ways that we can get the TCP IP protocol numbering, the addressing that we need onto this device. There's get it automatically with something called DHCP, and then there's get it manually or statically by us inputting the correct information. We can do this same thing for DNS. I have a nugget called DHCP and DNS, so we will elaborate on those particular protocols in that particular nugget. So let's say we want to put this information in manually. We go into the IP address field once we say I want to use the following IP address, and we say 192.168.1.16, and we can put these numbers in. Now, this numbering scheme right here is called dotted decimal notation. It is a 32-bit address that we break up into this dotted decimal notation. Instead of representing it as binary, 32-bit long binary number, that would be really difficult for us to work with as humans. So we break it up into decimal in this dotted decimal form. Now, the IP address is a unique number for this machine on the network, and then when we click in subnet mask, it automatically gets filled out with what's called a default subnet mask for this IP address. What the subnet mask is doing is it's breaking the IP address up into two parts. One part identifies the network, and that's the 192.168.1 part, which is identified by all 255s in the subnet mask. And then the host identifier or computer identifier is that 16. And notice that correlates to the 0 in the subnet mask. Now, if we want to communicate with other machines on this 192.168.1 network, we can right now just fine. But if we want to communicate off of this network, we need what's called a default gateway address. The gateway address, the default router, if you will, on my network is at 192.168.1.1. So I put that address in there so we can communicate particularly to the internet off this small office home office network. Now, DNS, the router at 192.168.1.1 can provide DNS services for me. Or, by the way, I could do an alternate. How about 8.8.8.8? This Quad 8, as we like to call it, is Google's DNS server out there on the internet. So this is a nice alternative if my particular router's having problems with DNS, and we can go ahead and rely on the very reliable Google one that is out there. So I've clicked close on that window and those settings were accepted, but did they work? Well, there's a really easy way to test that. I'll go to a web browser and I'll go to CBT Nuggets, and look at this, we can get to CBT Nuggets just fine. So we just verified that the IP address information that we entered into this machine is valid and is working great for us. Now let's go back in there and look at those settings, because there was actually something really pretty special about the settings that we used. So I'm going to right click and go properties, and then inside here, inside the properties window, I'm going to choose Internet Protocol version 4 and go to properties. So there's the settings that we entered. Notice the 192.168.1 is our network. And again, we can see that's our network because of the subnet mask in comparison to that. That is a private IP address. Let me go ahead and put on screen here all of the potential private IP addresses that we're allowed to use in our small office, home office networks. It turns out that we can use any address in the 10 range. So anything starting with 10 dots. So we could do 10.0.0.0 all the way up to 10.255.255. All right, let me just start over. Here we go. 10.255.255.255. So we call this the 10.x range because anything that starts with 10 for an IP address is private use only. We can use it all that we like inside our private networks. There's a 172.16 space that goes up to 172.31.255.255. And then finally, there's the range that we're using, 192.168.0.0 up to 192.168.255.255. So these addresses make plenty of addresses for us to use for internal use only purposes, for private networks only. Great. Out on the internet, these are not valid. So public internet, like web servers and things, you will not see addressed in this range. In fact, here's an example of one. It starts with 8. Notice that's not in any of these ranges, so that is clearly a public address. And I mentioned that's the public address for Google's DNS server. So this great concept of private versus public addresses exists for us to take advantage of. And by the way, if these addresses don't work on the internet, the address of my machine won't work on the internet, then my router at 192.168.1.1 does something called network address translation so that my machine can communicate out on the internet. This is so cool. So we have this router, and this router will literally take our private address and translate it into its public address for use out on the internet. That's how that functions. Now, there is actually a third category of IP address that I want you to know about, and it's called an APIPA address. I'll talk more about this in our DHCP nugget, but this automatic private IP address is what your machine would get if you're set up to receive it automatically, but there's a problem on your network and you can't get an address. Your machine will freak out and it'll say, okay, I'm going to go ahead and assign an address from the 169.254 range. So whenever we see our machine has an address of 169.254, we can pretty much safely assume there's a problem on the network. Now, wasn't it interesting when we put this IP address in that the subnet mask automatically got filled out for us? You see, this IP address is actually part of a group of IP addresses called a Class C address. So when it saw the 192, it said, oh, that's a Class C address, and the default Class C subnet mask is 255.255.255.0. So it filled it in for us. We can engage in what's called classless interdomain routing, or CIDR, and we can actually put in whatever subnet mask that we want as long as we follow some simple rules with that, and we can make whatever size networks that we want in here as long as we don't, break the mathematical rules of how many addresses would be possible. So just keep that in mind, that the subnet mask, sure, we can go with the default that is suggested, or we could design a network of a certain size and we could put in a classless mask, maybe 255, 255, 240, 0, for example. Now, there is a bit of a problem that has been addressed, no pun intended, by the designers of these technologies. You see this 32-bit address that we represent in what's called dotted decimal notation? Well, when they invented TCP IP version 4, they figured they had come up with an addressing scheme that accommodated billions of addresses and that they would never ever run out of these public addresses. Remember, we divide them into the public and private categories, as I mentioned, and they figured, yeah, we'll have enough public addresses, more than we'll ever need. Well, sure enough, that's not the case. The internet has gotten massive. With the Internet of Things, we like to connect everything to the internet now. Our lights, our appliances, our cars, everything is wanting an internet connection these days. So sure enough, we're running out of addresses. The solution for this is a new version of IP. So if we go in here and we say okay here, and we look in here, we'll see there's Internet Protocol version 6. They skipped version 5. That was left for experimental purposes. And now they've gone to version 6. And when you go into the properties for this, you'll notice it follows the same logic. We can get an IPv6 address automatically and get our DNS servers automatically, or we can use our own static assignment. Notice that the address field here is really long and the default gateway is really long, and that's because these addresses are huge. Remember we said in an IP version 4 address there's 32 bits? In an IPv6 address there's 128 bits. When you move an address from 32 bits to 128 bits, the number of combinations that you have gets massive. There's enough addresses here in IPv6 so that every single person on the planet could have billions of addresses. I mean, it's insane. You can't even wrap your head around how many addresses are available. And they're not even saying this time that this will be enough. They're just saying for the immediate future, we should be okay. So what does an IPv6 address look like? Well, let me paste one in here for us. And we can see it's a big, long address, and we can see we don't use dotted decimal anymore to represent this address. We use hexadecimal broken up into little portions. So it's a massive address. There's some ways we can shorten this address, by the way, a little bit. For instance, instead of all these zeros, we can put in a colon instead of just a single colon, and we can trim leading zeros. So there are ways to shorten the representation, but you get the idea. It's a big address space that is solving the IPv6 address shortage we currently face. Now let me cancel these changes and let me bring up something that might be bothering you at this point. Look at this. By default on my computer, I'm running both. Yeah, I'm running version 4 and version 6. Why? Well, all machines are starting to do this because what we're trying to do is make a transition away from IPv4. But we obviously can't do that all at once. We can't send out a memo, everyone, next Thursday the internet will be down at 4 p.m. as we transition from version 4 to version 6. That's not going to work. Internet's got to stay up. All these networks have to stay up. So we will gradually make the transition. And as we're doing that, all the machines out there will be running both version 4 and version 6. Gradually, we'll see version 4 shrinking and more people speaking just version 6, but we can leave both in place for a long, long time. Some say in our lifetimes, we won't see V4 go away. That's right. In our lifetimes, it'll stay around. There'll be pockets of it, and the V6 will just get larger and larger. So you and I looked at quite a bit in this particular nugget, and you can follow along, of course, with your Windows machine. You may want to watch this nugget twice. Watch it again as you follow along, checking out these settings on your own Windows system. We talked about IPv4 versus V6. We talked about static assignment versus dynamic assignment of address information. We saw the subnet mask we need to provide and the default gateway we need to provide. And again, we get to elaborate on these topics in nuggets to follow. Well, I sure hope you found this nugget informative, and I'd like to thank you for viewing.